Well, I am super proud of you. You guys made it through our day 41 concavity, and that was definitely a tricky one at the end. And now we're on to a much easier day. And I've actually got to tell you, I'm extremely excited. In the past, I've never had time to do concavity and the second derivative test on two separate days. This year, I was finally able to rearrange a few materials and was able to put these on two different days. Wow, it makes me so happy. So let's see how good of a job I did splitting this up. Our opener gives us a complicated first derivative. Now, we've seen first derivatives that look like this before. dy dx equals y times the cosine squared of x minus x plus 1. It's complicated looking. It's not great. However, we have seen derivatives when we've taken derivatives of implicit functions before, right? If I had something like x squared sine of y equals y, right? You'd take the derivative of each side, you'd get weird dy dx's, and when you finally finish isolating dy dx, you get something like this, where we say that dy dx is a function of x and y, which means that this is our output, and in order to find the output, we need two different inputs. We need an x and a y, and you see our two different inputs over here. Okay, let's begin. Your goal on this opener is to work through and determine first, is the point 0, -1 a critical point, right? We're going to use dy dx for that. And then second, once we decide if it's a critical point or not, spoilers it is the point a relative max or relative min? So go ahead, give that a shot, and then once you're done, unpause me and we'll see how you did. All right, hopefully you have enough time here, and let's take a look at what we probably did. Well, to determine if something's a critical point, then that means that either dy dx is going to be equal to 0 or dy dx does not exist. Inspecting this equation over here, this function, it looks like there's no value that would cause this to not exist. So I think if this point here is a critical point, it has to make dy dx equal to 0. Which means we should probably evaluate 0, -1 into dy dx. Now, this is kind of an interesting function notation here, but I'm basically going to say we're going to take dy dx and we're going to evaluate it at the point 0, -1. And so that means we take this equation and we replace everything with its respective value. So y is replaced with -1. Cosine squared I always like to rewrite as cosine of something squared, right? Moving the square to the far outside. And x in this case is 0, right? Minus 0 and then plus 1. Okay, well, let's see what we end up here. So working down dy dx of the point 0, -1, we get -1 times, well, cosine of 0 we need to remember is 1, and 1 squared is 1. Okay, minus 0 plus 1. It looks to me like if we're doing dy dx at this value, that we're getting -1 plus 1. So we get dy dx of 0, -1 is indeed equal to 1. Right, therefore, 0, -1 is a critical point. Because remember, the definition for a critical point is that's just a point that makes the derivative equal to 0 or not exist. Now, this would not be enough to justify, if this was the second derivative, it would not be enough to justify that 0, -1 was an inflection point. Because to be an inflection point, that's where we need to make sure that the second derivative changes sign. But a critical point is easier. A critical point is just, does the point make the derivative 0 or undefined? And in this case, it does. Cool. All right, well, part 2. Okay, now that we know it's a critical point, does that make it a relative min or a relative max? Well, in the past, to find relative mins and maxes, we made a sign chart, so we should probably do that. So we have this over here. We're looking on an infinite interval here. They didn't give us any endpoints. And I think the only x value, because we're talking x values here, the only x value they gave us was 0. And so we saw when x was 0, y was -1, but it made the derivative equal to 0. Cool, so we have our sign chart. This is, we're going to use the first derivative to test if an x value of 0 is a critical, or is a relative extrema. So then we need to take a value and we need to plug a value smaller than 0 into the derivative. So what's smaller than 0? You might say, oh, -1, -2. Well, that's really exciting, but if you take a value like let's just use -1 over here, right? That's this value right here. If we use -1 and put it into the derivative, that's fantastic, but what do we replace y with? Right? We get this -1 piece here, but what does y become? Because that can very much so throw off our answer. And so I think we can't do anything more. In fact, it seems like our first derivative, using that to test this interval, isn't going to be enough to tell us if our point's a relative min or max or neither. So what are some important takeaways here? Well, I think takeaway number one, and you guys should take notes as relevant, takeaway number one is that we had a derivative that might have been implicitly defined for the original function. So it's a derivative that had y and x, which means when we evaluated our point, we needed to use both y and x. You might want to jot that down. And second, when we had such a derivative, it wasn't enough to just have an x value because we need both an x and a y to evaluate the derivative. So our first derivative test actually fails here, which is a real bummer. Well, let's jump in then to the second derivative test and some reminders first. If x equals c is a critical number, and I actually like the version critical number more than critical point, because point we usually assume is x comma y, where critical number or critical value is just one specific number, but pretty much everyone says critical point to mean critical number, so it doesn't really matter. If x equals c is a critical number, then we know that that x value makes the derivative equal to 0, or it makes the derivative undefined, D&E if you will. And as we saw up above, knowing x equals c as a critical point does not provide enough information to decide if that location is a relative extrema. We'll take a look at the opener. But does that change if we know something about the second derivative, connecting everything we've done so far? Well, for example, let's say that c, which is our critical point, that's what made our derivative 0 undefined. Let's say that c is part of a graph where the graph is, f double prime is greater than 0. That means our graph is concave up. And you can see the u in concave up is kind of like a concave up graph. In fact, I should probably graph a concave up graph over here. Well, if this is my function f of x, right, f double prime just tells us that f of x is concave up, and we know that x equals c is a critical point, then where does x equals c have to be on this graph? Well, I think the only place on this graph where the slope is 0, or I think the slope is not undefined anywhere, and the only place where the slope is 0 is this spot down here. Right? That's where our tangent line is horizontal, the slope is 0. And looking at our graph and knowing that the point is down there, what can you say about this point? I think based on the graph, couldn't we say that that point is a relative minimum? So just by knowing the concavity at the critical point, then I think that might be enough. And we can actually do this the other way as well, right? If our graph is concave down, if f double prime is negative, and we know x equals c is a critical point, then this point right here has to be x equals c. That's the only space on the graph where there is a horizontal tangent line, and in turn that means then that this point has to be a relative max. So that's pretty powerful, combining the first derivative and the second derivative, and in fact that is the second derivative test. It's going to test our critical points using the second derivative. But think about what goes with this. It says we need critical points and we need the second derivative. That implies a little bit more work in terms of the calculus realm than we're used to. That means not only do we need to find our critical points by setting f prime of x equal to 0, or determining where f prime of x does not exist. Then we're also going to need to find the second derivative. So not only do you need to take the derivative once and do work with that, you need to take the derivative a second time. And once we take the derivative a second time, we're going to evaluate the critical point, x equals c, in the second derivative. And so we're going to evaluate that in the second derivative, and based on the outcome, based on the shape of the graph, we're going to know if that critical point is a relative min or relative max. You should note, though, that the second derivative test only works for critical points that make the slope equal to 0. Because if the slope equals 0, right, and I'll give you two different curves here. Let's say here's where the slope is 0. Well, that means that when you take the derivative of this point, when you find the next derivative, right, there's going to be some sort of curvature. There's going to be some sort of concavity. However, if you had a graph where the slope is undefined, maybe we'll do an absolute value graph, something like this, right? This is where the slope is undefined. So if f prime of c does not exist, and you take the derivative of something that does not exist, you want to measure the rate of change at something that isn't there, well then that derivative also will not exist. And if our derivative doesn't exist, then we don't know anything about the concavity. So our second derivative test is pretty limited. I mean, full disclosure, I use the first derivative test, what we did up here with our sign chart. I use that 98% of the time. There are only special cases where we really use the second derivative test because it's a little bit more work and it's limited. We need the slope to be 0, not undefined. But assuming the slope is 0 and not undefined, we should probably understand our conclusion here. If f double prime of c is greater than 0, so if our original graph f of x is concave up and we're testing this critical point, then clearly the critical point has to be a relative minimum. However, if the second derivative is less than 0, that means our graph f of x is concave down and our critical point must be here. That, of course, is a relative maximum. However, if f double prime of c is 0, right, and that is basically telling us that there is no concavity at that point, then we don't know the shape of the graph, and we unfortunately can't use the second derivative test. We say the second derivative test is inconclusive. And we've seen things like this before. We've found limits where we get 0 over 0. We've said it's an indeterminate form, so actually sometimes you'll see when the second derivative is 0, they say the second derivative test is indeterminate. You're unable to determine the concavity, or you know the concavity is 0, you're unable to determine if the critical point is a relative min or max, and you actually have to try the first derivative test. Now, the question you should be asking is, well, if we get an equation f of x equals stuff, and we have to take the derivative and then do all sorts of things where we set the derivative equal to 0, we solve, we figure out things, why would we want to find the next derivative? Why would we want to actually take the second derivative and then start plugging things into that if we could just do a sign chart? Well, and the answer is the end of that sentence. If we can just do a sign chart, a lot of times that is just not possible, right? And we saw an example on the opener, in fact, this example. Well, let's go back to it again. Is the point 0, 1 a relative max or min? There's two things that make this point a relative max or min, or at least using one of those tests. And in order to use the first derivative or the second derivative test, the very first thing you have to convince your reader of is that point a critical point? But luckily we did this on the opener. And the nice part is, this is the most work that you would have to show on a free response too. That says 0, 1. This should say 0, -1. Yeah, 0, -1. So that's awkward. I will fix that on your notes before you get there. So let's pretend it says 0, -1. I even wrote it over here. We know this answer. We did it on the opener. So I'm just going to say this equals 0. So I'm going to say, therefore, 0, -1 is a critical point. Cool. That's important because if you don't define that first, then you have no business using the first or second derivative test because you can only use those with critical points. So you do need to state that, right? Do you need to show the work to get from here to here? No, you don't. They want to see, they being the AP readers, want to see the setup and the answer. And if you can do all of this work in your head to get to the answer, bravo. We already did the work too. I showed the work earlier. So there's no reason I'm going to state that again. But what do we need to do next? Well, as we saw, a sign chart doesn't work. So I think the next thing we have to do is we actually need to find the second derivative in order to try the second derivative to test our critical point. So to take the second derivative, don't forget that we're going to do d dx of each side of our original equation. And you'll definitely want some room here. I've probably run out of room already, but that's okay. I can write smaller, I think, than you guys. So we're going to take the derivative of dy dx here. We're also going to take the derivative of y times the cosine, and I'm going to rewrite this as the cosine of x squared minus x plus 1. All right, so taking the derivative here, well, remember we kind of abuse this notation and just multiply our fraction straight across, even though that's not really what we're doing. So we're saying this becomes d squared y over dx squared, the second derivative, equals. To do the second derivative of the right side, I think we're probably going to need the product rule for the first part, aren't we? The derivative of y is, of course, dy dx, right? And then we're going to keep the second one the same, so that's cosine of x squared plus, now we keep the first one the same, and then we multiply by the derivative of the second. This is always a nice reminder of how to do cosine squared. The 2 comes down, cosine stays the same, and we go to the first power. So all I did is I took the derivative of the squared first. But then our chain rule says we need to do the derivative of the inside, which becomes negative sine of x. Cool. Now let's finish off the rest of this. Derivative of negative x is negative 1, and the derivative of 1 is just 0. Probably don't need to put that, but that's fine. Great. Now we have the second derivative. How do we perform the second derivative test? Well, what we really need to know is what is the concavity at this critical point. So essentially what we're saying is we need to take the second derivative and we need to evaluate the second derivative at the given point, at the point 0, negative 1. Well, as we go through, we already know the value of the first derivative at 0, negative 1. It's a critical point, right? This means plug 0, negative 1 into the first derivative. We already found that that was 0. We did that on the opener as well. This becomes cosine of 0 squared, okay, plus y is negative 1 times 2 times cosine of 0 times, oops, let's put the negative out here. Actually, I think 2 negatives will probably end up turning this into a positive, won't it? So we'll get rid of the negative. That's always nice, being able to erase. Sine of 0, and then we end with minus 1 at the end. So I'm just going to work to the right because I've somewhat run out of room. 0 times anything is 0. Sweet. Sine of 0 we know is 0. So this is 0 times anything. That's 0. And then we're subtracting 1. So I think we just get negative 1 here. Nice. Well, this is actually a conclusive answer because what we've done is we've not only shown that there is no slope here, but we've also shown that the graph is concave down. And full disclosure, I don't ever have this memorized. So I always, when I find the graph is concave down, I go through and I draw a concave down graph and then plot the critical point. Well, that critical point is clearly a relative max, so now I can write my conclusion. Okay? As 0, negative 1 is a critical point, and dy dx at 0, negative 1 is less than 0, right? You could say this, oh, that's not right, not dy dx, oh man, d square y over dx squared. The second derivative evaluated at 0, negative 1 is less than 0. You could just say the second derivative at that point is less than 0, is negative, whatever sounds good to you. Then 0, negative 1 is a relative max. I do see a lot of people mess this up. They think, oh, second derivative negative. Negative means min because mins are smaller than maxes. Just draw yourself a picture and you'll be just fine. The second derivative test tends to be more efficient than the first derivative test because I only had to plug in one value. That was really nice and get one answer. Versus the first derivative test, if I wanted to fill in this sign chart, I would need to plug in a value here and over here. So I'd actually need 2 values to the 1. However, there are some additional efforts we need to make here because it's only going to be more efficient if you're given the second derivative equation. Otherwise, you need to take the derivative again, which is just as much work as plugging in a point. If you're able to find the second derivative equation really quickly, right? If we had like x squared, y prime was 2x, and you're like, oh, y double prime, that's 2. That's super easy, right? Why not use the second derivative test? Or, and then C is the big one, you don't have enough information about the first derivative. And that is what we saw in the opener. We only had the point 0, negative 1. We didn't have any other points, so we couldn't figure out intervals. The AP exam is very fond of just giving you a critical point, like we did earlier, and the second derivative and saying, tell us using the second derivative, is this a relative min or max? And if you forget the second derivative test, that becomes extremely tricky, if not impossible. Just reminding you of the first derivative test, always nice to have them both on the same packet. You find your you find your critical points the same way that we would for the second derivative test, nothing bad at all. We create a sign chart. Right? And once you have the sign chart, you want to use f prime. It's all about the first derivative to test points in each interval. And then last but not least, you write a conclusion about what's in the sign chart. And of course, you don't reference the sign chart. So nothing too bad. So this next part then is going to give you guys some practice. There's just 2 nice pages for you guys to go through and work that second derivative test. None of them particularly relate to each other. 1 is a standalone, 2 has an A and a B, 3 has an A and a B, 4, right? So what you should do is try all of them first, or if you want, you should try 1 and then make sure you're doing it correctly. Or again, try all of them, and then if whichever ones you get stuck on, go back and watch the video and we can see how you did. All right, hopefully you've had enough time to work through this. So I'm just going to go through each one individually, and we'll see what we can do. Let's see, so unknown function, first derivative, f of 0 is 1, relative min, max, or nothing at 0. Well, the first thing we need to do here is make sure that this could possibly have a relative min or max. So we, I think, need to evaluate our derivative, dy dx, at our point, which is an input of 0, output of 1. So we get 1/2 of 0 plus 1 minus 1. That looks like 0 plus 1 minus 1, which is 0. Good. We always need to check that first to make sure this point is a critical point. If it's not a critical point, then it's automatically neither, and we're done. So very, very important. We should also realize, though, that in order to find more points on the first derivative, and sorry if you hear some squeaking, my dog has decided it's squeaker o'clock, we need more points on this derivative. But unfortunately, we only have this point right here, so that is a huge bummer. So then we would probably go ahead and try the second derivative, because the second derivative, we just need to use this point. We're not looking at an interval. So to find the second derivative, we're going to take the derivative ddx of the first derivative, and I'm going to again keep working left to right here just so I don't run out of room. Let's see, our first derivative was dy dx on the left side and 1/2 x plus y minus 1 on the right side. So I'll draw a little arrow. So we get the second derivative is equal to, and let's see, 1/2 x just becomes 1/2, y becomes dy dx, and minus 1 becomes 0. Cool. It's honestly a nice idea too to just replace dy dx. Don't forget that we know dy dx is equal to 1/2 x plus y minus 1. So I'm just going to replace that for simplicity. So we get 1/2 x plus y minus 1. And that gives us a nice clean second derivative that only is an input of 2 variables instead of having a third variable here too. Okay. So then I think our last step is we need to evaluate our second derivative. We need to evaluate it at our critical point to tell the concavity of the function at that critical point. So it becomes 1/2 plus 1/2 times 0 plus 1 minus 1. And again, you'll notice that we saw this before. The first derivative becomes 0, but we get a final answer of 1/2. So what does that tell us here? Well, I would draw that graph. 1/2 means concave up, positive concavity. And we're looking at a critical point, and the only way that can happen is down here. So our critical point then must be a relative min. Okay? And don't forget, please, your conclusion. So conclusion, nothing too bad, as 0, 1 is a critical point, and d squared y over dx squared at 0, 1 is greater than 0, positive, right? Then 0, 1 is a relative min. The picture helps, I promise. Alright, second problem. Suppose we have some function where we know a couple things about it, all these things about the graph of f, and then they give us g prime. Oh man. First, show that the second derivative of g is given by this monstrosity. Well, we have the first derivative of g up here, and they're asking us about the second derivative. I think that means we just have to take the derivative. Now, I'm going to take the derivative using the product rule, right? We can see that 2 functions are multiplying, red and purple in this case. So when I do the derivative of the left side, that will become g double prime of x. The right side, well, we're going to do the derivative of e to the negative 2x, which is e to the negative 2x times the derivative of the power. And then we're going to keep the right side the same. 3f of x plus 2f prime of x. Very nice. Plus, then we're going to do, we're going to keep this first one the same, e to the negative 2x, and we'll take the derivative of the second. This won't change too much because 3 and 2 are coefficients. They're just multiplying, so they stay. We can do the derivative of f of x, though, which is, of course, f prime and our f double prime. All right, well, unfortunately, that still doesn't quite look like this guy, but we might notice that they have this e to the negative 2x factored out. So let's take that e to the negative 2x and factor it out front and see what that leaves us. So continuing the colors here, we have e to the negative 2x times, and then that leaves me, and I'll bring this negative 2 down here, so negative 2 times 3 f of x plus 2 f prime of x. And then the other piece is plus, and then we've just removed the e to the negative 2x. We might as well, we can keep the parentheses for now, but really you could drop them, nothing bad, like that. And then we have our ending piece over here. And hopefully if I clean this up, I'm going to end up with this on the inside, but we will find out. So g double prime of x, e to the negative 2x is still hanging. This is negative 6 f of x. And there's no more f of x's to combine it with, so I think it just stays. This is negative 4 f prime. Negative 4 plus 3 more is going to give us negative 1 f prime. And then there's nothing to combine with these two f double primes, and you are hopefully breathing a deep sigh of relief because that does match our g double prime. We've done well so far. What type of local extremum, if any, does G have in x equals 0? Well, the if any is important. We should first make sure that G has the potential to have a local extremum at x equals 0, which means we need to determine if x equals 0 is a critical point or not. So we should probably go through and determine what is G prime of 0. And so that is using our equation back up at the very beginning, right? So it's e to the negative 2 by 0. 3 times f of 0 plus 2 times f prime of 0, and I'll just work to the right. We see that this is e to the 0th, nothing bad, and then f of 0 and f prime of 0, they were kind enough to give us at the beginning, weren't they? So f of 0 is 2, f prime is negative 3. Okay, so I'm looking at 1 times 6 minus 6, 1 times 0, which is 0. Oh, good, that's awesome. That means that this is a critical point, so there is a chance that there is a relative min or max. If we knew other points, we could totally keep using G prime and make a sign chart, use the first derivative test, but they give us very limited points, just exactly what happens at 0, not around 0. So I think we'll probably use our second derivative to test our critical point. So let's move on to that second derivative and see what happens if we evaluate the second derivative at 0. Negative 6 times f of 0, and again we're just using our equation that's right up here, so nothing too bad, minus f prime of 0 plus 2 times f double prime of 0. I'll work to the right, e to the 0th, negative 6, we already found f of 0, that was up above, I think that was 2, and then we get a minus coming next. F prime of 0 looked like negative 3. And then f double prime of 0, where is that one? Oh, f double prime of 0 is 0. That makes the math really easy. Very exciting. So we end up with 1, and then this is negative 12 plus 3 plus 0. Negative 12 plus 3, I think, is negative 9, so we get a negative value. Okay, again, quickly sketching a picture. Concave down, f double prime is negative. Critical point, relative max. Justify that response. Keep that practice going. You only need one sentence every time you do these justifications. So as g prime of 0 equals 0, and thus x equals 0 is a critical point, and easy for me to write, and g double prime of 0 is less than 0, then x equals 0 is a relative max. And some people ask, well, wait, should we state the test that we're using? These tests are kind of informal names. I mean, everyone knows them, and you could say by the second derivative test, by the first derivative test, but you really don't need to name them. Just giving this information is enough to tell the reader that you actually know what you're talking about. All right, 2 problems to go. Consider this derivative. Let y equals f of x. So again, they're telling you that y is some function of x. So it's y equals like 6x squared minus cosine of x, something like that. But they're just giving you a very vague original equation. But the original equation to the given derivative. It's known that the line y equals negative 2. What does that look like? Well, the line y equals negative 2 is this line down here. Right, goes kind of straight across, pretty good line too, is tangent to the graph of y equals f of x. However, they didn't actually tell us where it's tangent, which is a little frustrating. And then it says find the x-coordinate at the point of tangency. Well, that's kind of tough because if our original equation, which I'll do in yellow, goes up here and kind of bounces off the graph, that could be a tangent point. But what if it bounces off over here? Or what if it, just looks like this? I mean, where is it actually tangent? Well, there's one other thing that has to happen at a point of tangency, and that's that they have to have the same slope. So basically what this is telling us is if our graph is tangent to y equals -2 right here, then they have the same slope, and we know the slope of y equals -2. The slope is 0. It's a horizontal line. That's pretty nice then. So basically what that's saying is if we take our derivative, dy dx, equal to 3 minus x divided by y, we know 2 out of 3 variables in this problem. We know that dy dx is 0, right? There's a slope of 0. We don't know the x, but we also know the y value. Of course, the y value has to be -2 at this point over here, right? It's something comma -2. So I know the y is -2. Now we have an equation with one variable. We could probably solve that. So think about cross multiplying, getting rid of the -2, whatever sounds good to you. That's going to give us 0 equals 3 minus x, which I think tells us that x is 3. So therefore, we know at the point 3 comma -2 on this original graph, and actually I drew this pretty well, 3 -2, there is a point of tangency. So who knows what the graph does? Maybe it looks something like this, but there is that point of tangency. Does f have a relative max, min, or neither? Well, don't use my picture as a guide. I mean, what if I drew my picture like that? Then it's a relative max versus a min. I don't know. I'm just making up the picture. We don't have any other points on here, though. We don't know what's happening on either side. So I think we'll probably use the second derivative at this point as well. Right? Usually if your first derivative is defined implicitly, you'll need the second derivative test. Oh, second derivative of that, though? Man, that looks like a quotient rule to me. What a bummer. But that's all right. So we have to go ddx of the left side and ddx of the right side. And notice I'm very careful to apply ddx to each side of the equation. I find if you don't do that, a lot of students lose where their second derivative is. They lose one side of the equation and they get really confused. So let's try not to do that. So 3 minus x divided by y, dy dx, and I'll work top to bottom here. So we get d squared y over dx squared, and then quotient rule. So we'll start with the top. Derivative of the top is 0, and then x is -1. We keep y the same, minus 3 minus x, and then the derivative of y with respect to x, dy dx, all of this divided by the denominator squared. Can we clean this up? I certainly think so. There's two ways that I'm going to clean this up. The first way is I'm just going to simplify as far as I can, right? This just becomes negative y over here. The second way is I'm going to replace dy dx with that guy up above. So we end up with the second derivative of y with respect to x is negative y minus 3 minus x times, and then dy dx is 3 minus x divided by y, all divided by y squared. And I'm really not going to do anything more than that. I don't think it's probably necessary here. So let's go ahead and actually use our second derivative to test our critical point. So the second derivative evaluated at our critical point, which we found up above, 3 negative 2, looks like this. It becomes negative 2 minus 3 minus x, that's 0, times 3 minus 3 divided by negative 2, that's also 0, over negative 2 squared. Well, this whole thing just becomes 0, so we, I think, are looking at positive 2 in the numerator and 4 in the denominator. I think they're both positive. That looks very positive to me, positive 1/2. So I think then we're dealing with a graph that is concave up, critical point, therefore this point is a relative min. And I've run out of room here, but I imagine you can write the same conclusion that we've been doing. Alright, and we're on to our fourth problem here. This fourth problem has gone through a couple renditions, so you might have seen originally the problem looked slightly different than this, but I think this one is the winner. This one's a little bit more straightforward, maybe a more common problem, a nice throwback to the last few days. So let's go through it. They ask us to find the locations of the critical points. We might as well start there. Eventually we'll have to justify if the critical points are local extrema, but critical points we've been doing for a few days. I think we just need our first derivative here. Don't forget that when we take that first derivative, we will certainly need our product rule for this first part. So we have our 4x, keep natural log the same, and then we add on, this is our 2x squared, keeping that the same, and of course natural log's derivative, 1 over x, and the derivative at the end, minus 6x. There is a little bit to clean up here. So we have 4x ln of x. I think 1 over x times 2x squared, I think one of those x's is going to cancel there and gives us a 2x and then minus 6x at the end. You might notice that that very nicely comes to a minus 4x, which is not a coincidence because now I think we can continue to factor and take out that 4x from each piece, which leaves us here. Cool. Normally we start with where f prime of x equals 0. I'm actually going to start with the does not exist piece, and then we can get back to where f prime of x equals 0. And the reason I'm doing the does not exist is because we're dealing with natural log here, and we need to remember with any log, you can never take the log of 0 or negative values. So f prime of x is going to not exist for any x that's less than or equal to 0, which what that really is going to show up as is a graph, and I'm going to erase this shortly. What it really means is that if x is any value over to 0 here, nothing's going to be here. There's going to be no graph. So what that's really telling me is that my original graph, which I'll probably show in red, is just going to take up this space on the right side. Okay, so it's not that there's an infinite number of critical points. They're really just telling us if you have this interval, it means that back up in the original graph, you probably have a very similar restriction, and of course we do because we have natural log up there. Since you have natural log, there's going to be nothing on the negative side of the x-axis, only on the positive. But there could be more critical points on the positive side, so let's see what happens when we set f prime equal to 0. I think we get 4x equal to 0, or natural log of x minus 1 equal to 0, x equals 0, or a little bit more work here, but nothing too terrible. Don't forget to undo natural log. We do e to the power of each side, and that gives us x equals e to the first, which is really just the number e. Remember, that's our 2.71828, so on and so forth. Okay, so it looks like we have two critical points. However, you could argue that there's really only one critical point because x equals 0, we aren't even allowed to evaluate in this equation. It won't make the equation equal 0. As soon as you substitute 0 into this part, there's going to be nothing there at all. So since there's no point, and since the interval we're going to be looking at is just from 0 to infinity, not including 0 because x can't be 0, you could make the argument that x equals 0 is probably not a critical point because it's not on the graph, right? X equals 0 isn't here, and it's just the beginning endpoint, and although you could maybe sometimes make the argument that critical points can be endpoints, probably the only critical point that would be on the multiple choice question is just x equals z. They never try to trick you up and say, is x equals 0 a critical point? Haha, no it's not. It's on the end of an interval. They wouldn't go that far. They just wouldn't give you that option as a multiple choice answer. So it looks like there's only one critical point here, x equals z. Well, then we come to a bit of an impasse where we say, well, okay, so far today we've been doing the second derivative test. So should we take the second derivative and then evaluate the second derivative at e? Well, of course, knowing me, I'm actually going to do both and then let you guys vote on which one you thought was easier. So let's start with the first derivative test. It's been a little while since we've done that one. And so I'm going to break this up into two parts. So we have our first derivative test. And remember, to do our first derivative test, we're going to be using the first derivative. We only need to look from 0 to infinity. We want to see the signs of the first derivative. We already know one of the signs is e, and that makes the first derivative 0. All right, well, we need to try a value between 0 and e into this equation over here. And usually the easiest value is another fact of any log we need to remember. Any log of 1 is 0. So I'm going to go ahead and try f prime of 1 over here. So f prime of 1 becomes 4 times 1 times the natural log of 1 minus 1. So this becomes 4, 0 minus 1. I'm thinking this is going to be negative here, isn't it? 4 times negative 1, we get a negative value. All right, well, let's try something on the right side. Whenever we're using natural log, there's only two types of numbers I like to plug in, 1 or e to some power. And the reason I like e to some power, well, you'll see why I like e to some power in just a second. So in this interval over here, I'm going to go ahead and try evaluating f prime at e squared. 2.78 to the second power, think of it as 3 to the second, somewhere close to 9, a little bit smaller than 9. So it becomes 4 times e squared times the natural log of e squared minus 1. Well, this is clearly positive. Okay, natural log and e cancel, and that just leaves us with 2. Right, the exponent comes down. 2 minus 1 is also positive. A positive times a positive is a positive. And so by using that power of e, we not only knew everything over here was, say, positive, but we also knew that natural log would cancel e and just leave us with the power. So I think that tells us then that our original function that I said I would do in red, but then started using other functions in red, so let's do it in, we haven't used purple yet, we'll do it in purple. The original function will decrease and then increase. So it seems to me that e is a relative min. But that was the first derivative test. What about the second derivative test? Well, we need to start with the first derivative, right? And our first derivative, you could write it anyway, but I'll just use my most simplified form here, was 4x times the natural log of x minus 1. So our second derivative, we do need the product rule here, but I'll use all one color. 4 natural log of x minus 1 stays the same, 4x stays the same, and this becomes 1 over x minus 0. And so keeping this as factors as I can, 4 natural log of x minus 1 plus, let's see, these cancel, so plus 4. All right, we could actually factor out a 4 from both of these too if we wanted, but I'm actually noticing if I distribute a 4, I think this will clean up very nicely. 4 natural log of x minus 4 plus 4, which means that our second derivative is just 4 natural log of x. Awesome. How do we use the second derivative test? Should have labeled this. This is our second derivative test. Well, we just evaluate the second derivative at the critical point. We don't need to test 2 points. We just do it right at the critical point and say, what's the concavity there? Our critical point occurred when x was e. Natural log and e cancel. They make a 1, so we just get 4. The second derivative is positive. Here is a concave up graph when the second derivative is positive. Here is my critical point. Can we see that that's also a relative min? So comparing and contrasting here, it's really up to you. You might have tried the first derivative test and said, well, wait, I don't know actually how to evaluate or pick a number that works on these intervals. I may get stuck here. And so you might be able to see that the second derivative test, although sure you had to use the product rule once, isn't too terrible. And then evaluating this at e is actually really, really nice. It gives an easy answer there. So I'm not saying that I would probably use the second derivative test. I'd probably just force my way through the first derivative test. But the second derivative test is very usable. Is it easier or maybe more needed when you can't find other values on the first derivative? Of course it is. However, don't forget that you always have that option. And then the last thing I have for you is just the graph here to make sure we're right. So I graphed 2x squared ln of x minus 3x squared, and we're looking to make sure that this point at e comma something, is a relative min. So pulling up my graph over here, here's the graph. Notice right at 0 it's undefined, that's an endpoint, and there's nothing on the negative side. That's not too much of a shocker. We already talked about natural log not being of negatives. And then if I jump down here, here's my relative min, and actually if I zoom out it looks to me like that's also an absolute min, but we talked about that before, and hey, look at that, 2.718. We should probably recognize that as an approximation for e, so e is indeed our relative min. Thank you again for our second derivative test and you guys tuning in and working so hard. Please, as always, ask me any questions through email, through Teams, whatever works best for you. I'm excited to see you guys back next class.